scancel, so we operate with the concepts. GRE was initially programmed on Wednesday. It's the last speaker of the session.
The title of my talk is the numerical procedure for the solution of writing process based on the energy space criterion. This work, yes, okay. This work was performed in collaboration with Professor Leguillon at the University of Paris. So as you know, we can predict the growth of microcracks by using a suitable energy criteria such as the Griffiths criterion. However, this criterion is not enough, not sufficient to predict the crack initiation. In order to overcome this shortcoming, Leguillon has proposed energy space criterion that combine the energy criterion in fractal mechanics and the space criterion in resistance of materials. They concluded that when fracture occurs, both this criteria have to be fulfilled along the crack path. This criterion is physically reasonable. Its efficiency has been proved by a large number of fracture cases studied in its region. However, all these studies have to be performed case by case by using particular solution technique, and also the crack path has to be known previously. All these factors limit the application of this energy space criterion. So we believe it is necessary and useful to implement this criterion into a numerical so that we can consider more general fracture problems. That is the main motivation of this work. So in this work, we have implemented this criterion into a 2D finite element code. The main algorithm is as follows. First, we localize the zones in which the strain criterion is fulfilled. For example, we have here 4 such zones. In each such zones, we have one and only one local maximum of the maximum principal space. Then we try to draw the potential fracture passes in all these zones. Next, we can calculate the energy release rate GI for different crack path combinations. Yes, that's one. And we choose the maximum values of GI and compare this value to the material stiffness. If we have max GI larger than GC, we create a new crack. This is the main algorithm. Now we explain some techniques used in this algorithm. First, we have to find all the zone. First, we have to find all the zone, all the zones in which the stress criterion is fulfilled, and in which we have a local maximum epsilon 1. To this end, we use a technique named watershed flooding technique. We explain this technique with a 1D example. First, we inverse the sign of sigma 1 and consider minus sigma 1. This is the variation of the minus sigma 1. First, we enter the point where magnitude 1 is minimum here, V plus water source. And by increasing the water level, we find the neighboring elements, and then we create the first catchment basin. And by increasing the water level, another distinguished local minimum is formed, from which we create the second catchment basin. Yes. And when the first and the second catchment basins meet, we plus a dam. This dam is so-called watershed line. And by continuing this process until sigma y equals sigma c, we can find all the distinguished catchment basins containing each a local minimum of minus sigma y. This is the technique to find all the zones in which the stress criterion is fulfilled. This animation is so as watershed flooding process. We do find 4 distinguished zones, such zones. And now we explain the techniques to draw the potential crack path and how to create a crack by element elimination. First, in each such zone, we find the element where sigma 1 is locally maximum here. And then from this element and the perpendicular to the division of sigma 1, we draw a line, a small length, dl, by using this sample formula. And thus we can draw successively in the 2 directions the small lines to determine the crack path in this zone. To create a new crack, we just remove the element where the crack pass through. Of course, we can use other more elaborated technique to create a new crack. Now we have a lot of potential cracks. Which cracks will be the real one? We assume that among all the potential cracks, the real crack will be that making the maximum change of the total potential energy, the united creation. So we just calculate the total potential energy before and after the activation of this cracks, and we calculate the energy release rate DI, and we choose the maximum value and compare it with the material roughness. If we have G larger than GC, we create a new crack accordingly. Now just present some examples for the validation of this numerical tool. The first one is a plate with a central crack. We just present half of the structure. This near deep crack tip region. The green zone represents the elements in which the stress criterion is fulfilled, and the red zone represents the element to eliminate, and the black zone represents the element, the field element that forms the crack. And we calculate the stress intensity factors for different crack lengths, and when we compare it with the Kc of the material, we can see that for the cracks, long enough cracks, we have K over Kc equal to 1. That's to say that in this case, the energy stress criterion is equivalent to the L1 Griffiths criterion in fractal mechanics. The second example is a plate with 2 edge cracks, and the red lines are the passes obtained in the literature, and consider that as a theoretical prediction. This animation shows the crack progression obtained by using our numerical tool. You can see that they are really close to the theoretical one. In order to examine the mesh independency of the algorithm, we have used 3 different meshes with different element size. You can see that all the numerical results are very close to each other and very close to the theoretical prediction. This is the global response of the plate, global strain space response plate, obtained with the 3 element meshes, and you can see that they are very close to each other. Here we next one. They consider the cracking in fiber reinforced cross-ply laminates, studied experimentally by Paris. And here we have a tensor test on a cross-ply laminate. We have 2 outliers with the fiber parallel to the tensor direction. And we have 1 inner ply with the fiber perpendicular to the tensor lobe. And the onset of the microcracks appear in the inner ply. We can see from this figure, when the inner ply is thick, that is a stress criterion predominating. While when the inner ply is thin, that is strain, this energy criterion which is predominating. And the numerical result reproduce well this transaction, and we will agree very well with the Harvard experiments result. This is a crack path of time with our numerical tool. Of course, these cracks appear each after another in a perfect tectonic manner. This result is very well with the analytical analysis of looking. Last example is engineering application. We try to simulate a woven ceramic matrix composite and uniaxial tension. This is the simplified 2D element mesh, in which we have several materials, matrix, ceramic matrix in red, longitudinal strength in yellow, perspective strength in green, and also have teeth. We compare just the strain stress response of time. Compare just the strain stress response obtained by the simulation and the experiments. Here they compare the acoustic emission measured in the experiments and the total crack length obtained in the numerical simulations. From these 2 figures, we can see that the numerical tool reproduces quite well the global response of the composite. Conclusions. In this work, we have implemented the energy stress fracture criterion in a 2D finite element code, which basically can predict both the crack initiation and the crack growth. It can also deal with multi-cracking problems. We have shown the mesh independency of the numerical model, because all the calculations are linear, have no conventional problem. The future may be the development of homogeneous model more operational numerical tools to give us more complicated problems such as 3D, nonlinear, and so on. Thank you.